All right, so we're doing a dispersion of the Prism Derivation lab. So we got to look at first, we're trying to figure out the deviation angles. Sorry, we're trying to find out the total deviation. And we do that by finding the individual deviation angles. So D1 right here is the angle of deviation from the incident ray, and D2 is the angle of deviation of the emergent ray. So we're going to write that, number 1, step 1 over here. So the total D, total angle of deviation is D1 plus D2. So, because the angle of incidence is composed, angle of incidence composes D1 and R1, and that the angles are always respect to the normal, and we're assuming that this way is positive, this way is negative, that the angle of incidence is equal to I minus R1. Sorry, the angle of incidence. D1 right here is equal to I minus R1. So I'm going to write that over here. That's what D1 will be equal to. And next we're going to do D2. D2 is the same thing, but with the emergent ray. So if we want to find D2, it's just E minus R2. E minus R2. And sorry, I forgot to explain. R1 and R2 are the angles of refraction. And R1 is right here, angle of refraction. The angle of refraction of the incident angle of refraction of the emergent angle. So, D2 so, however, we still got to do D1 plus D2. So, this is I minus R1 plus E minus R2. So next, I'm going to do a little bit of factoring with the negative signs. And we're just going to have, there's a D in front of this. This D is equal to I plus E minus R1 plus 2. Remember, it's just I did some factoring to get out the negative there. It's just I plus E minus R1 plus R2. So if I know I can calculate R1, and this is where Snell's law comes into place. I can conclude R2 by doing geometry. And we can calculate E by applying Snell's law. So, speaking of geometry, what we're going to do is now we're going to get rid of R1 and R2 to make it so it's not R1 plus R2, it's just its own variable. We can represent R1 plus R2 as something. So, R1 plus R2 really it's really R1 plus R2, but we don't need to focus on this part of the triangle right here. All we need to focus on is this top half of the triangle. So we assume it's a triangle, it equals to 180 degrees. And so what we're going to do is that, these are the two angles of refraction right here. And so, assuming from this same thing that we did with the calculating D1 and D2, we're going to do the same thing but for these sides right here. The reason why these are 90 is that when I draw these angles of refraction, it creates a 90-degree angle here, but also the triangle is equal to 180 degrees. So this is 90 minus R1 for the angle of incidence refraction, and it's 90 minus R2 for the angle of emergence refraction. And this is all equal to 180, and we're just going to call it A. And that's what our variable is going to represent R1 plus R2, because that's effectively what this is R1 plus R2. And we're just going to draw that over here, or write that over here. So what we're going to do is we're going to do A plus 90 degrees minus R1 plus 90 degrees minus 2 is equal to 180 degrees. And then let's do some simple math right here. All we're going to do is cancel out the 90s, cancels out 180, and then we're just left with, up top on step 7, I'll put that up here. So step 7, it's just A is equal to R1 plus R2. But now we have what A is equal to, and that is, and we're very happy about that. So next what we're going to do is we're going to sub it back into what the D equals D1 plus D2, and we have what D1 is equal to, we have what D2 is equal to, and now we have what R1 plus R2 is equal to. So now we can put that into our equation. So we have, sorry, technically it would go into step 5. So step 8, it's D is equal to I plus E minus A. So next what we're going to do is we're going to figure out, based on Snell's law and a graph of, so this graph right here is, put it a little closer. This graph right here is graphing deviation as a function of the angle of incidence. So basically what it's trying to say is that as the angle of incidence, and then to explain this graph, where I got it from, so I was watching the video. Basically what he was saying is that this is a computer simulation of this graph. And then based on this graph, we're able to validate and use Snell's law to then derive to get the equation that we need. And so to do that, we notice that as the angle of incidence increases, the deviation decreases, then increases again. But what we're interested in is the minimum value. And so what we can see on this graph is that if we draw 2 points up, right here and right here, this, I'm trying to draw it so it's equal in height. So we have 2 points on the graph where the angle of incidence, where the deviation angle is the same for each angle of incidence. So you might be saying, like, yeah, but we're trying to find the angle of incidence and emergence, but I'm going to explain that using Snell's law really quickly. So let's say we have, we're going to look at right here, we're going to look at the top graph right here, and I'll bring it up here. So what we're looking at is that we have, this is going to be our angle of incidence, and go through, this is our angle of emergence. And this is our angle of deviation right here. So, and we have all the lines and whatnot. So, question is that based on the principle of reversibility, can this be flipped the other way and we get the same result? And yes, based on Snell's law and the principle of reversibility, if we change the angle of incidence to be 50 degrees, and then we have an angle of emergence as 20 degrees, we get that they're the same, but we just have the angle of deviation on the other side. So, and then as you see, these two, this angle right here and this angle right here are just two separate sides of the same angle. And then to show that graphically, to show that as kind of like a combined version, I have it right here, is that this shows kind of like we have an angle of emergence, angle of incidence. They're both going, like, you know, if we have one going in here, coming in here, it shows that we have an angle of emergence, incidence, and that it doesn't matter the angle of, geometry and Snell's law don't care about the direction of the incident ray. So if we have 20 degrees, 50 degrees, it's going to look the same. And then and then these two angles right here are equal to each other. And that's based on Snell's law and the principle of reversibility. So this gives you a little bit of background into what this graph is trying to tell you. So let's say this right here is one angle of incidence. This is another angle of incidence. But sorry, I can't see it. That's one angle of incidence, that's another angle of incidence, right? But what we're talking about is in terms of the angle of incidence and the angle of emergence. So, but this looks familiar, right? Because we have, for the same deviation angle, we have they're the same, the deviation angle is the same for both incident rays. And what I said before is that geometry and Snell's law don't care about the direction of the incident ray. And what I showed graphically is that, with the angle of emergence and the angle of incidence, is that they can have the same angle of deviation. And because the angle of emergence and the angle of incidence have the same angle of deviation, we can confidently call this one as the angle of incidence and this one as the angle of emergence. However, now there has to be a point to where there is a minimum angle of this system. And so where this system right here is equal to is that at this point, I is equal to E, or the angle of emergence is equal to the angle of incidence is equal to the angle of emergence. So there's only one point where the angle of incidence equals to the angle of emergence, and that is at the deviation minimum. All right, so now that we know that the angle of incidence is equal to the angle of emergence by this graph right here, we're going to figure out how to actually get to the equation that we want. And we'll do that by talking about Snell's law. And so we're going to bring back the equations from before. And those two equations will be d equal to I plus E minus A. That's the angle of deviation. And then we're going to bring back A is R1 plus R2. And based on Snell's law, these are equal to each other. There's the principle of reversibility. And this triangle right here, R1 and R2. We can see that. Yeah. R1 and R2. It's the principle of reversibility. So, now because they're equal to each other, and because the angle of emergence and the angle of incidence are equal to each other, we can say, and I'm just going to create my my own variable here. So d is going to be equal to, we're going to make this as I naught. Or, I naught. Let's do, let's do I naught. And this is minus A. And then A itself, because R1 and R2 are equal to each other based on Snell's law, I'm just going to call that R naught. So A is just equal to R naught. So in order to find and then now we can actually write Snell's law itself. So it could be, it's the sine theta 1 equal N1 sine theta 1 equal to N2 sine theta 2. And because, assuming it's air, it's going to be 1 times sine the angle of incidence, it's I naught, and then equal to N, because going into the glass, sine, and then R naught. So, next we got to solve for I naught and R naught, and to solve for I naught, we're just going to do so d minimum, and d minimum comes from minimum deviation angle. Right here. That's our d minimum. So dm or d minimum. And then what we're going to do is, let's say d minimum is equal to 2i minus a. And you're like, where does that 2i come from? Well, the 2i comes from the fact that you have I plus E. And if we say I naught is equal to the angle of emergence and the angle of incidence, then it's just two of the same thing, so it's just 2 times I naught. So it's 2 minus sorry, 2 I naught minus A. So if we solve for I naught just plus A, and so we have D minimum equal to I naught divided by 2 divided by 2. Then we have I naught is equal to, I'll show in a second, I naught, forgot the plus A. Plus A is A plus D min over 2. I hope you can see that, A plus D min over 2. And then after that, we're going to solve for A itself. So A is equal to 2 R naught. But we got to find what R naught's equal to. So we divide by 2, and then R naught is equal to A over 2. So now we can plug R naught and I naught into our Snell's law equation. So I'm going to write that over here. So what I'm going to do, I'm going to write, so this is, I forgot the steps, but this is sine of A plus dm over 2, and then this is equal to n sine A over 2. Now, I'm going to erase this stuff right here so I can show how this equation is still equal to the same one that we want. So I'm going to erase this. So what we want to get and what was given to us to derive is n prism over n naught equals sine of 1/2 plus theta sine of 1/2. So, what we're going to do now is I'm going to show that this equation right here is equal to this equation right here is equal to this. So what we're going to do is we're going to divide sine A over 2 into both sides. So erase this. And then after we do that, it's going to be, show it here, n equals sine A plus, get a better chalk thing, it's getting bad. A plus dm over 2 over sine A over 2. Then what I'm going to do is that based on the top equation up here, sine 1/2 times those variables plus that. But as you can see here, is that all of these are over 2. So what I can do is I can just pull a 1 over 2, because this is basically, this is all over 2, or it's 1/2. I'm just going to pull that out, pull that 1/2 out. So it's going to be sine of sine 1/2, and then it's going to be A plus dm over. Now, same with this part right here. Just going to pull the 1/2 out of this. Pull the 1/2 out of this right here. So this would be sine 1/2 times A. So I'm going to have to write more room to show that it's equal to this. So say it's equal to n. So I just all I gotta do now is shuffle some variables around, and then it should equal to it. So now what we're going to do is that we're just going to replace the variables with the ones we were given by the equation we're supposed to achieve. So in Prism, equal, so we're going to plate, so it's still sine 1/2, instead of A, we'll do the variable given, plus, should be the little delta, right, I'm just going to write a little squiggle, over sine one half times the other variable. And this is over n naught. And then, so that equation right there is equal to the goal equation. And the only mistake I made in derivation, this is supposed to be inside the parentheses. Should get that, I'll fix that real quick. So, and yeah, that is it. Thank you for watching.